Hello class, this is CSE 4600, section 62, week 10, fall 2024. Good news, not only did I fix the artifacting on my setup, but I also got it to fill the whole screen. So now we have an even larger view with which you can hopefully see everything that I do. Okay, so midterms should be all said and done. You should see grades hopefully as early as sometime this weekend. I will discuss the answers to that a little bit this coming Monday. I just need the time to, grade everything. Because, after all, this is a size 90 class. Anyway, with the midterm all done and dusted, let's go back to chapter 2 for a little bit so we can check out one of the classical synchronization problems that was brought up. So there were 3 different synchronization problems, like 2 or 3 of them. One was the reader's writer's problem, and another one was the dining philosopher's problem. Yeah, reader's writer's problem, the producer's consumer's problem, and the dining philosopher's problem. We're gonna look at one of those. I originally wanted your next lab. So this is your next lab now. I originally wanted your next lab to be all about inter-process communication, but I couldn't get the pipe to work, so I just said to myself, screw this. Let's try something else that's a little bit more fun. And hopefully, on the other hand, hopefully this also gives you really good experience with how to work with p-threads as well. If you ever enroll in CSE-5250, which is most likely going to be taught by me, you're probably going to need to know, you're going to need to know p-threads as well. So, we're going to implement an instance of the producer's consumer's problem using p-threads. So, I'm going to pause the video so I can bring back the PowerPoint slides so you can get a refresher of what the producer's consumer's problem is. Okay, so remember there were like 3 different problems regarding synchronization. One of them was the producer's consumer's problem, also known as the bounded buffer problem. If you recall, the idea was as follows. We have 2 processes, one is a consumer and the other is a producer. There is a shared buffer that each process can access. One process, the producer, adds stuff to the buffer. The other one, the consumer, takes stuff from the buffer. This idea of producers and consumers also generalizes to any number of processes, but if you recall from the slides, we started with 1 of each, so 1 producer, 1 consumer, so a total of 2 processes. So, if you recall, the problem with the bounded buffer problem is this. If the producer tried to add to an empty buffer, nothing wrong would happen. It would just fill up as it would. But when that buffer fills up and the producer tries to add stuff to it, it can't. Well, it shouldn't, I should say. In that scenario, the producer should go to sleep, and then the consumer will come in, take stuff from the buffer, and then send a wake-up signal to the producer, telling the producer, hey, wake up, there's space in the buffer now. You can add stuff to it. Conversely, if a consumer were to take from a full buffer, nothing wrong would happen. But if a consumer were to take from an empty buffer, that's where you get also problems, because how can it take anything from a buffer in which there's nothing to take? I guess what could happen is it would try to access memory it shouldn't, and then we'd have even more problems at that point. But the consumer shouldn't try to take from an empty buffer. If it tries to do that, the consumer will go to sleep, and then when the producer comes in and adds stuff to the buffer, it'll send a wake-up signal to the consumer telling it, hey, wake up, there's stuff in the buffer now. So if you recall, those are the issues with the bounded buffer problem. There were also a few race conditions we had to solve as well. The solution is to have those sleep and wake up signals. Processes go to sleep and then they receive wake up signals later on. The problem is there may be a race condition in which in which the CPU scheduler may decide for another process to run. One process thinks the other process is asleep, and it sends a wake-up signal, even though it's not asleep. It was in the wake queue for the CPU. That signal for wake-up gets lost, so we need a means of saving those wake-up signals, and that's what... So that was the point of a semaphore. So the solution to the banded buffer problem may look something like this. This one uses semaphores, but in pthreads we're not going to use semaphores. We're instead going to use something else. They're called condition variables, and it's just another way of solving the producer's consumers problem. So we're going to take a step-by-step approach of, well, actually writing the thing. So with that, I'm going to open a whole new terminal, and I'm going to type in, well, there's several ways you could do this. I'm not familiar with the word editors on Ubuntu, so what I generally just do is I open up. What I personally do, because I'm not familiar with all the word editors in Ubuntu, is I just type in vi and then file name. I'll call this pcp.c. PCP is short for Producer's Consumers Problem, of course. There's like one other thing called PCP in the context of computer science. That's Post's correspondence problem. But you won't see that until like CSE-5000. My point is, there's like two different PCPs here. But we're working with a different one. So I guess a better abbreviation would be BBP for banded buffer problem. But I called the files PCP because, well, that's just how I called it first. Whatever. I'm gonna type in vi space pcp.c, press enter, press escape, press :WQ, and now I have my text file. That will now become my source file. So this is gonna become an implementation of the producer's consumers problem. And that should not be a pound sign, that should be a double slash. I guess I was thinking about Python code and I used the wrong comment. I used the wrong comment character for that. Okay, fixed. Okay. So you do have instructions on Canvas outlining what you are to do with the producer's consumers problem. That is your lab 2 instructions. And again, it's all step by step. Much like the last lab, I highly advise you do this on a Unix machine. So a Mac, a Linux machine, the lab computers in Jack Bryan Hall, or remotely accessing said computers. Or what I personally like to do is use a Linux virtual machine. It doesn't matter what machine you use as long as it works. You could get it to work on Windows, but for consistency's sake, I'm just gonna, like last time, use a Linux machine. Okay, so we need quite a few things for this. So, part 0 of your program, and the lab's instructions literally is all step by step. So this is part 0 of the instructions. So the 0th step is to add all of the necessary headers, so all the include directives needed for our program. So, # include standard io.h, include standard lib.h, include pthread.h, because we are working with pthreads after all, and finally, include UNI standard.h. I believe that's Unix standard. There we go. We also need to define a whole bunch of variables because, well, some of these are going to be important for enforcing mutual exclusion, but some of these are just going to be things that we're going to be using to tweak later on so you can, play with the program. And oh yeah, we need a buffer as well. So you need to define the buffer. So I'm just gonna do it like this. Define buffer size 10. So the buffer is of size 10. The buffer will hold 10 items. I'm also gonna create the buffer here. Because this is something that must be shared between every thread. Oh, by the way, the discussion of the producer's consumer's problem had the producer and consumer be different processes. However, we are instead implementing them as threads. Same functionality, different implementation. Because of that, we're not using something like a pipe to send information between one process to another. We're instead using shared memory. And because the buffer is shared memory between not processes, but threads, it's gotta be a global variable. So I'm just gonna define a buffer of buffer size. So now we have our buffer. It's an array that's gonna hold some numbers. We also need another variable called count. That tells us how many things are in the buffer right now. At this moment, the buffer is empty, so the buffer is, well, 0. Let me just add some comments. I'm not sure if you're seeing the lines bouncing a little, but I can. Maybe it's subtle enough that it's not so distracting, but just warning you right now. Okay, so that is the buffer. We define how big the buffer should be. We define the buffer itself, and then we have an extra variable that says how many things are in the buffer right now. Now we need a few more things. Okay, so when it comes to mutual exclusion, we have a little thing called a mutex that we can use as a lock. So this lab's a little bit, well, this lab uses both a mutex and 2 different condition variables. It may be a little bit confusing, but let's just roll with me here. I do have another lab in CSE-4600 where students there are just using the mutex by itself. They're using that in the context of enforcing mutual exclusion. It's just that we're not only doing that here, but we also need the condition variables to tell these threads, hey, the buffer is empty, or hey, the buffer is full. So we need to use one mutex and 2 different condition variables. One to say, hey, the buffer is full, and the other one that says, hey, the buffer is empty. Or rather, not full and not empty. You'll see how. So the data type for a pthread mutex is, well, pthread mutex t. So that's our lock. We also need 2 condition variables. So the data type for that is pthread cond t, and this one is not full. And I'm gonna cheat here and just copy paste this one line, not empty. Okay, we're almost done. We also need to define... Okay, so basically we don't want this program to run forever, rather we are gonna have it run for a set amount of time. Basically, the producer is going to produce some number of items, and the consumer is just going to take those items out one by one. However, one of these things here, we're using that to slow down the operation of these threads to simulate production and consumption time. Here's how. We're gonna say it takes 1 second to produce an item and then 2 seconds to consume an item. So basically, when a producer adds stuff to the buffer, it's going to sleep. It's gonna go to sleep, not in the sense of the sleep operation from the slides, but it's just gonna stall itself for 1 second and then add another item in the buffer. Similarly, the consumer is gonna take something from the buffer. It's gonna stop itself for 2 seconds, and then it's gonna take another item from the buffer. Okay, we're almost done with defining all these variables. How many items will each producer make? Int num items equals 10. And finally, how many pairs of producers and consumers are there? Basically, we're gonna start with just one pair. So int num thread pairs equals 1. So basically, we have the program set up so it will create an equal number of producers and consumers. I guess one interesting variant of this particular implementation is having different numbers of producers and consumers. Say there are more consumers and the producer is slowly filling up the buffer. Consumers are taking stuff out of the buffer faster than the producer can fill up the buffer. That would be an interesting variant. Something I would also encourage you to experiment with as well. For simplicity's sake, we're just gonna limit ourselves to the same number of producers and consumers. The only difference is how fast they can make and take items. We're gonna change these values later, by the way. Okay, so all of that was part 0. So part 1, that is the code for the producer. Let's get started with that. So this is the thread function for the producer. So now we have void star producer, void star arg. Okay, so remember the little weird thing about void star? That's basically a pointer that we can cast to any other kind of pointer. We are gonna pass in something into this function, but that something is just gonna be a thread identifier. We're gonna be basically passing in a number that the thread is gonna use to identify yourself with. So when we eventually create these threads, when we have these threads, we're gonna not only pass in the producer function, we're also gonna pass in a number that's gonna use to identify that thread. So when that number gets passed in, we have to get that. So here's how we do it. So int ID equals star and int star arg. Okay, so now we have our thread ID. Because when these producers produce stuff, for the sake of showing what these threads are doing, every time a producer adds something to the buffer, it's gonna say producer number whatever, just added an item to the buffer. So that's why we want that ID. We want to tell which producer is doing which, even though in this case there's only one producer and one consumer. Okay. We want to add stuff to the buffer. So, add stuff to the buffer. We have defined how many items a producer is going to add to the buffer. We define that using num items. So, for int I equals 0, I is less than num items I plus plus. So this reveals a little interesting thing about this implementation of the producers consumers problem. This is, let me add. Because of how this is set up, there's always going to be the same number of producers and consumers. Because of that, the number of items that each producer is going to make is going to be balanced out by the number of items each consumer is going to take. So if you wanted to vary the number of producers and consumers, we got to be careful here, because if we have fewer, if the producer makes fewer items, because of how this code is set up, if the producer makes too few items and the consumers want to keep on taking items, if we programmed it so that the producer is producing fewer items that the consumers are going to be programmed to take, we're going to have some problems here. But anyway, I guess that's itself a whole other programming challenge, to try to rewrite this so we can have arbitrary numbers of producers and arbitrary numbers of consumers. But, for example, they rely on global variables that says the producers and consumers are gonna collectively, not individually, collectively take some number of items, produce some number of items and then take some number of items. That would be an interesting variant of this implementation. But for now, for simplicity, as I said, same number of producers as consumers, and they're all each going to make the same number of items and then take the same number of items. So when we add stuff to the buffer, what items are you going to add to the buffer? Well, I guess a simple thing we could do is have it so that when this producer adds stuff to the buffer, it's just going to add numbers. Add the numbers, put the numbers 1 to num items into the buffer. So int item is going to be I plus 1. Okay, now we need to acquire that lock, because that buffer is a shared thing after all. Acquire the lock. pthread mutex lock, pass in the address of mutex. And that's how you use a mutex, by the way. We are missing one step, but we're gonna cycle that when we get to the main function. But when you use a lock, when you use a mutex is the same as a lock. When you use a mutex, you gotta acquire the lock by calling something like lock. In this case, it's pthread mutex lock. So once you acquire that lock, we're allowed to enter our critical section. However, there's a few more things to do before we even do that. If the buffer is full, wait for it to empty out. So while count equals buffer size, we're just gonna wait here for that buffer to empty out. So in that case, I'm gonna have printf producer %d is now waiting for buffer to empty out. And then I need to pass in the ID. There we go. And then we're gonna wait on this condition variable not full. So we are waiting because this buffer is full, and we're waiting on a condition variable that's called not full. So, to wait on a condition variable, we have wait. Or more specifically, pthread cond wait. Pthread cond wait. We pass in the address of that condition variable, not full. And we also pass in the mutex as well. Okay. Now with that, we can proceed to the next step here, and that is add an item to the buffer. And we're gonna simply say buffer count plus plus equals item. So this is a bit of terse code here. It's basically two things that going on here at once. Basically, count is the number of items in the buffer, but we are also using that as the index of the element in which we're going to add our next item. So this could be separated into two lines, something like this. Buffer count item and then count plus plus. This works too. It's just that if we do it like this as one line, it's going to evaluate it as such. It's going to add an item to the next available slot in the buffer, and then that count is going to increment by 1. That's just a one-line implementation of the previous setup I had here. It can work like this as well, down here. But then again, this also works. This is just a terse version of the same. Same thing, different numbers, different amounts of lines of code. Next, we're going to say printf producer %d has added to the buffer %d \n. So then we have to pass in the ID and the item. So basically, this producer has produced an item, and then it's gonna say what that item was. It's also gonna need to signal to. It's also gonna have to signal to the consumer if the consumer was waiting for an item in the buffer because the buffer was empty at the time. The producer must now send a signal to the consumer through the other condition variable called not empty. So if the buffer was empty, signal to the consumer that there's an item in the buffer now. So pthread cond signal address of not empty. And then we're gonna release the lock. And we do that by calling pthread mutex unlock. When you take CSE-4600, I do get into greater detail into all of these pthread functions. Not necessarily the ones related to condition variables because, well, currently right now for CSE-4600, I don't get as far as I do here. but maybe I will adjust the material sooner or later so that we do get into greater detail with condition variables, because I feel like this is important for you to know. Also, the way I do my classes is I always have it be more on the side of projects. You learn more by doing stuff than you do just sitting and listening, because sitting and listening gets boring after a while. If I have you do something on your own, like follow the instructions, understand how these lines of code work, that experience of building something that works, I feel like that's a much greater learning experience for you. But at the same time, I feel like it better teaches you how these things work. Yeah, sure, you can learn how to program, for example, a video game by looking up how the functions work. But it's one thing to look up the inputs and outputs of functions than it's one thing to learn the inputs and outputs of a function. It's a whole other thing to, actually use them. Anyway, we're almost done. Sleep to simulate production time. So sleep. It's a little bit confusing because everything's on the left side of the screen, but it's also at the bottom corner. So I just added a whole bunch of space too. Okay, added a little bit of space to just move everything up towards the top of the screen. There we go. Okay, so that's the end of the function. Return no, and that's it. We've written the consumer. No, we didn't write the consumer yet. We just wrote the code for the producer, but now we need to write the next code, and that is for the consumer. So this is now part 2. It's more or less the same thing, except we gotta make some changes to the code. So I cheated here a little bit by copy-pasting the producer code. Now we are dealing with the consumer code. So now, add stuff to the buffer. Instead of not add stuff to the buffer, take stuff from the buffer. So now the consumer isn't producing anything, so we don't need to have this thing here. So we're just gonna skip that and acquire the lock. If the buffer is full, that only applies to the producer. If the buffer is full, the producer can't add anything to the buffer yet. However, if the buffer is empty, the consumer can't take anything out of the buffer yet. So, let's flip this code around. If the buffer is empty, wait for it to fill up. So while count equals 0, consumer %d is now waiting for buffer to fill up. And now we're not waiting for the not full condition variable, we're waiting for the not empty one. There we go. Take an item from the buffer. So, not this, but rather this line of code. So, int item equals buffer, left square bracket, minus minus, count, so what does this first line of code do? Well, it's gonna decrement the count, and then it's gonna decrement the count by 1, and then it's going to access the item at that index. So the count is the index. So if the count was at like 3, we have to go back 1 to access the item at element 2. That is our item. So basically what this is is a terse version of the following. Minus minus count, and then int item equals buffer count. What the minus minus at the front does is it decrements, and then we do stuff with the variable. If we put that at the end, it's gonna do stuff with the variable and then decrement. That's the wrong order. We want to decrement it and then do stuff with it. Well, here's the other thing. If we just separated this out and just have the count here, if we just separated this into two lines, then we're doing whatever we do in this one line of code. It doesn't matter whether we do it put the minus minus at the front or the end. Because we're not really doing anything. The only thing we're doing on this line is decrementation. That's it. But to follow the terseness of the code that I have here for you, let's just put the minus minus in here. So int item equals buffer minus minus count. Now that we've taken the item from the buffer, now we can print it out. Print f. Oh yeah, I have a print statement here. So consumer %d has taken from the buffer. It's gonna print out its ID, and it's then gonna print out the item that it took. Okay, if the buffer was full, now we need to signal to the producer. If the buffer was previously full, we gotta signal to the producer that there's space for a new item now. So we need to signal not full. And then we gotta release the lock, and we're gonna have this consumer go to sleep. We're gonna say sleep for however much time we defined here. So it's gonna sleep for 2 seconds. Okay, so now we have the thread function for the producer and the thread function for the consumer. We're almost done. The next thing we're gonna do is write the main function. And it's this main function. This is the main thread that's going to create all the other threads. It's gonna start them all up. And then those other threads, the producer and consumer threads, they're gonna produce stuff and put stuff to the buffer, and the consumers are gonna take stuff from the buffer. So here's where things get fun. We're gonna int main and now we're gonna initialize our thread handles. So p thread t producers num thread pairs, and also p thread t consumers num thread pairs. So in CSE-4600, the text book that I have for that calls these thread handles. It's just a thing that we use to have a handle to our thread. Much like how you have a file handle when you're doing anything with a file. For example, when you open a file in a program, that's actually the very first thing that you do to a file before you do anything else to it. You have a file handle, and you use that to specify, I want to do stuff with this file. And there's a whole bunch of behind the scenes interestingness that in CSE 4610 explains why we call open for a file before we do anything with it. But the point is this: that handle is a pointer that points to somewhere in memory, and that somewhere in memory has information about the file itself. And that information is basically where on the disk is that file. So that's what I mean by a file handle. So basically that's what's meant by a file handle. Similarly, we have thread handles. Okay, so now that we have our thread handles, we need to initialize our mutex and condition variables. When we initialize a mutex, there is a pthread function for that. It's called pthread mutex init. We pass in the address of our mutex. And for the second one, we're just gonna pass in null. We also need to initialize our two condition variables. Pthread cont init, that is the function. We're passing in the address of one of our condition variables for the first argument, and the second argument is also null. And then I'm just going to cheat here and duplicate the line. So pthread cont init not full, and then pthread cont init not empty. There we go. Okay, so here's the next thing we need to do. We need an array of thread IDs. Not thread handles, but thread IDs. So this is just an array of numbers, and those numbers are, we're gonna pass in those numbers to our thread functions, and it's those numbers that the thread functions are gonna use to identify, hey, I'm thread 1, or rather, I'm consumer 1, and then I'm consumer 2, and then I'm producer 1, something like that. So we're gonna make another array here. And because we've set it up so there's the same number of producers and consumers, it's okay, in this case, for us to have this one array be used for both the producers and consumers. If there was a different number of producers and consumers, we'd need two separate arrays. And then I need a for loop. And then I'm just simply gonna say thread IDs I equals I. So this way our numbering scheme starts from 0 because, well, in a lot of things in computer science, everything's, most of the time in computer science, everything starts from 0 rather than 1. If something starts with 1, it's a little bit off. Yeah. If stuff starts at 1, it may throw things off by 1. We have a special class of errors in computer science and just programming in general that is called the off by 1 error, an OBO. So, basically, if you haven't gotten used to starting counting from 0, you gotta get used to it now. Unless you're specifically like working with Lua or MATLAB, those are some of the few languages that start counting from 1 rather than 0. Anyway, so now that we have our thread IDs for our producers and consumers, now we can create our threads. And we create a thread by calling pthread create. We pass in the address of our thread handle, and then we pass in null, and then we pass in the thread function, and then we pass in whatever arguments are to be passed into the thread function. So here's how it works. We pass in a thread handle, and it's going to be the address of producers I. And then null, and then producer. When we pass in the name of the thread function, we're just passing in the name itself. We don't have to have the parentheses or anything like that. And then we pass in the address of thread IDs I. So that way, if this is producer 1, we're gonna pass in the thread handle for producer 1 and then pass in the ID for producer 1. Okay, so now we have a producer thread created. Now I'm gonna cheat here and copy paste that same line and then have it for our consumers. So consumers I, and then not producer, consumer, because we have both a producer thread and a consumer thread. We make producers and consumers in pairs, or at least that's how we define it here. If we have different numbers of producers and consumers, we would need separate arrays for their respective thread IDs. It also means we would need 2 different for loops, one for the producers and then one more for the consumers. So if we had it so that we could have different numbers of producers and consumers, we would need 4 for loops here, not 2. Actually, we would need 6 because the final for loop that we need is calling pthread join. So if we wanted to have different numbers of producers and consumers, we wouldn't need 3 for loops, we would need 6. 6 for loops. 1 for the thread IDs, no, 1 pair for the thread IDs for the consumers and producers, 1 pair for the pthread creates, and 1 more for the pthread joins. Yeah. So 2 for the thread IDs, 2 for the pthread creates, and then 2 for the pthread joins. Since it's programmed so that we have the same number of producers and consumers, we can get away with 1 for loop for each. So for int I equals 0, I is less than num thread pairs I plus plus. Before I continue, I'm gonna add a little comment up here. Join threads. And now I can say pthread join producers I null. And then pthread join consumers I. So these are our thread handles from before. Okay, so now our threads have joined back with the main thread. The last thing we need to do is some cleanup. So previously you it's probably been some time since we looked at the last slide, but I think I had it so that you were doing dynamic memory allocation, or maybe that was CSE-4600-62. Actually, due to special circumstances, I had to reuse the same lab for 4600 for 5250, so I believe it was the case that you had to dynamically allocate memory for your thread handles. We're not doing that here, so there is no need to call any functions for allocating or deallocating memory. So there's no malloc and there's no free, because you don't need them. Because we've hard-coded the number of threads that we need all the way up here. And because of that, we have all the memory we need already. No need for memory allocation no need for malloc, no need for free. So that's why when we do our cleanup here, we're only cleaning up the mutex and the condition variables. Once we're done with our mutex and our condition variables, we gotta destroy them. So let's do that. So let's do some cleanup here. Pthread, mutex, destroy. Pass in the address of mutex. Similarly, pthread cond destroy. Pass in the address of not full. And I'm just gonna cheat again and copy paste that line. And pthread cond destroy, not empty. There you go. And now, return 0, and that's the end of the program. Now, moment of truth. Will this program work? So the command to compile the program, I'll just expand this a little bit so you can see the whole thing. That is gcc pcp.c -o pcp, short for producers consumers problem, -lp thread. It worked! All we gotta do is type in // into the file name, and it's working. So now, we get to see the producers and consumers adding and taking stuff from the buffer. However, it's only just one producer and one consumer just taking turns adding and taking stuff from the buffer, but the producer and consumer are adding and taking at different rates. So at some point, the buffer is gonna fill up, but here's the thing. I said at some point the buffer is gonna fill up, but it's currently set so that the number of items being made and taken is 10. Even if that number is the same as the number of items, even if the number of items being made and taken matches the size of the buffer, it's never gonna fill up to the point where the producer is gonna have to go to sleep or the consumer is gonna have to fall asleep, because it never fills up completely. So now, this is part 1. This is one of the first screenshots you have to do, showing the program running. Okay, so the next step, as specified by your lab, is we're gonna change the number of items so that we try to get the buffer to fill up. Now remember, because of the produce and consume time, it takes more time to consume an item than it takes to produce an item. So that means if we just increase the number of items being made and taken to some high amount, let's say it's 40, if we just did that, at some point the buffer is now gonna fill up entirely. Let's see it. So now I have to recompile the program. And we run it. You can see a sort of pattern in which the producers and consumers are adding and taking stuff from the buffer. Basically, the producer is adding adding two items to the buffer for every item the consumer is taking out. And now we've reached a point where, check this out, the producer is adding items faster than the consumer is taking items out. So now it's to the point where the consumer has to wake up the producer because the producer had to fall asleep had to go to sleep because it couldn't add stuff to the buffer. It's working. Interesting the order in which items are being added and taken out. So now we're now at the items that were just added like very early on. And now we have item 2 being taken out. I wish there was a way to visualize this, because I guess a visualization would be really neat. More so than just a textual display. But let's do another experiment. So, second deliverable, your second screenshot for this program is, well, to increase the number of items being made. Let's not do that next time. And instead, let's increase the number of producers and consumers. Let's do 5 each producer and consumer. We're gonna clear, and then we're gonna recompile the program and rerun it. Oh, the buffer just filled up perfectly. So now there are 5 times as many producers and consumers. They're all adding to the buffer faster than the consumers are taking stuff out of the buffer. The overall effect is items are being made and taken faster now, because there's now 5 threads making and taking stuff. 5 threads each for the producers and consumers, all adding and taking stuff from the buffer. So because of that, the program just ran faster. Because they're all making and taking stuff from the buffer all at the same time. But still, it's still the case that the producers are making stuff faster than the consumers can take. The producers are making stuff faster than the consumers can take. What if we flip that around? So that's your last screenshot that I would like for you to take here. So we're gonna clear once again, and then we're gonna go back to our code. We're going to change it so that let's do 5 pairs of producers and consumers, but we're gonna swap the produce time and consume time. Now the producers are adding. Now the consumers are taking faster than the producers can make. Let's see what that looks like. So let's recompile the program and run it once more. Now the consumers, because the consumers are taking stuff faster than the producers can make, now the consumers are going to sleep because there's nothing to take. Yeah, this is basically the essence of the producers and consumers problem. And again, it would be really neat to see both scenarios happen, but we would need to do some further modifications to this program so that we would need to do some further modifications to this program. Perhaps give each producer and consumer randomized produce and consume times, so we could see both scenarios happen, where the buffer fills up completely and the buffer empties out completely. How it's set right now is that we'll only ever get one of the 2 possible messages. That is, the buffer just filled up, the buffer just emptied out, and the consumer has to wait for it to fill up. Or, the buffer just filled up, and the producer has to wait for the buffer to empty out. But yeah, this is all pretty neat. I guess one more variant we could do, and I'm just gonna do this for fun. This is not asked for in your lab, but I'm just gonna try it out anyway. The produce and consume time is the same, but there are 16 producers and consumers. So the idea is, now the buffer's gonna fill up really fast. I'm just doing this for fun. You don't have to do this unless you really want to try it. Let's see if this runs just fine though. Consumer 6 is now waiting for the buffer to fill up, and Consumer 6 has taken an item from the buffer. Waiting for buffer to fill up, waiting for buffer to fill up. Waiting for buffer to fill up. I guess at one point, it decided that Consumer 1 had to run next, and then it tried to take for an empty buffer. So I guess we can try to imagine the order in which these threads were executing, because on this virtual machine I have a limited number of... On my main computer, I have some amount of resources, and then that some of which is going straight to the virtual machine. So this is an 8-core 16-thread CPU with a whole ton of drives and a super beefy graphics card. I don't think the graphics card is contributing any resources to the virtual machine. What I do know is that some of the system's memory here, and CPU cores, is going to the VM. So yeah, really interesting, don't you think? Anyway, so your deliverables ask you for 4 different screenshots in addition to the program and like 2 different questions for you to answer. Basically, the screenshots are for the first run where we just went with the default parameters, the second run where we have more than 10 items to add to the buffer, and then 10 items to add to the buffer, but with 3 of each producer and consumer, and finally swapping the produce and consume times. So yeah, I think an interesting variant of this would be if instead of having a predefined produce and consume time, we instead had a random number generator that would randomize the produce and consume time. Wouldn't that be neat? But then we'd have to change our messages even further. So it would, for example, produce just made an item in 3 seconds, and then it would also output the producer ID, the item that it had made, and the production time. Similarly, we would have to do something for the consumer, where it would have to be like, consumer just consumed an item in 5 seconds. That would be a very fun variant of the producer's consumers problem, where every thread has random produce and consume times. And hopefully that way we can see both scenarios, we can see both situations pan out where the buffer is completely full, and then later on the buffer is completely empty. If the buffer is full, the producers can't add anymore. If the buffer is empty, the consumers can't take anymore. So yeah, pat yourselves on the back if you've gotten this far and you've gotten it to work, because that is the basis of Lab 2. Hopefully, by next week, you'll see a grade for your midterm, and I'll also discuss the midterm answers as well. With that, I'm going to end it here, and then we're going to convene once again next week, and hopefully look at the next part of your... We're going to look at the next chapter of your textbook, and that is all about memory. So, with that, I'm going to end it here, and then we're going to look at memory next. Alright, take care. Have a good day.